You are listening at a moment when the sky is carrying a story you were never promised to witness. A story that wasn't supposed to happen in your lifetime. It's late November, and while most people are focused on the shortening days and the weight of another year winding down, something far quieter has been unfolding above you. A visitor from another star, an object older than every mountain on Earth, older than every ocean, older even than the sun, has begun its final approach. And in just a few weeks, on December 19th, it will pass closer to our world than any interstellar object ever recorded. You may have clicked on this because you've heard fragments of updates online, numbers that don't match, images that look different from week to week, comments from people who are confused or anxious. You may simply want clarity. You want someone to explain what's actually happening without panic, without drama, and without the noise that tends to follow anything unusual in the night sky. You've lived long enough to see how quickly information gets distorted. You've watched the internet turn quiet events into loud ones, and loud events into something unrecognizable. But beneath all of that, you still carry the same quiet curiosity you had when you were younger. The part of you that once stared up at the sky and wondered what might be moving out there and how close it might someday come. Tonight, you'll get answers rooted in what astronomers are measuring right now. Not last month, not last year. Right now, in the final days of November, as new data arrives each night. NASA has released updated brightness curves. Amateur telescopes have picked up changes in the shape of its tail. There are subtle shifts in its behavior that don't quite match the textbook expectations. And that's why so many people are talking about it. Not because something is wrong, but because something rare is unfolding, and time is running short to study it. You'll hear the real picture tonight, calm, complete, and steady. You'll understand what this object is doing, what it isn't doing, and what will actually happen on December 19th. And as you follow its path, from a world beyond our sun to the quiet stretch of sky passing over you now, you may find that the most extraordinary part of this moment is not danger, but the simple fact that you are here to witness it at all. You may not have seen the beginning of this story, because the beginning happened far beyond the reach of every telescope ever built. Long before 3i Atlas appeared in the faint November images that first revealed it, long before its name began circulating online, it was already on its way toward you, quietly, steadily, across a distance so great that your mind can only touch it the way your fingers touch the surface of a cold window. You are meeting it at the very end of a journey that likely began near another sun, in a region colder and darker than any place inside our own system. The proof of that doesn't come from imagination, but from the physics written directly into its path. Its orbit is hyperbolic. That single detail changes everything you think you know about comets. A hyperbolic orbit is not a looping path, not a curve bent back toward the sun, not the kind of journey that brings a visitor home again. It is an open arc, a farewell gesture, a shape that passes once and never repeats. For an object to follow such a path, it must travel faster than the sun can hold, moving above escape velocity, free from the gravitational net that binds planets, asteroids, and long-period comets alike. You are not watching something that will circle back in 100 years or even 1,000. You are watching something that is simply passing through, just this once. There are other clues as well. 3. Dove into the plane of our solar system at a steep, unusual angle. Too steep to match the thin, orderly disk of objects formed around the sun. Its incoming speed, measured long before it reached the warmth of the inner system, was already higher than any bound object should have, and its trajectory, when projected backward through decades and centuries, fails to intersect with any region where solar system bodies typically originate. Instead, it points out into the dark between stars, a direction with no familiar landmarks, no traceable family, no gravitational signature that could have launched it from here. This is why astronomers were immediately certain. It did not come from our sun. It came from someone else's. The only other objects like it that humans have ever seen were Oumuamua in 2017 and Comet Borisov in 2019. You might remember the debates that followed them. The strange, non-gravitational motion of the first, the bright, rapid outgassing of the second, the arguments that erupted because both slipped past our instruments too quickly to study in detail. They were brief, incomplete encounters. They left more questions than answers. 3I, Atlas, is different. It is brighter, closer, slower, relative to Earth. For the first time, you are watching an interstellar visitor with enough time, enough data, enough cooperative geometry for scientists to study without rushing. This is the closest interstellar object approach ever recorded, and you are alive precisely when it's happening. To trace its path, astronomers reconstructed its motion by running time backward, calculating where it must have been years before we ever noticed it. That reconstruction leads away from the sun, away from every orbit known, and out into interstellar space. Its past does not match the long, stretched ovals of comets born in the Oort cloud. It does not match the gentle inclinations of Kuiper belt objects. Its history is a straight, clean line from the dark. Michelle Bannister, who helped classify Oumuamua, once described such visitors this way: interstellar objects don't knock, they simply enter, and it's up to us to notice. NASA is paying such close attention, not because of fear, but because this object carries chemical fingerprints from a place we have never sampled. Its dust, its ice, its trapped gases, all formed under a different sun, in temperatures and pressures unlike the ones that shaped our own planets. Each molecule is a memory from another system. Each grain of dust has drifted through cosmic cold for millions of years before arriving in the narrow cone of space where Earth can study it. Scientists want these clues because they expand our understanding of how solar systems form, evolve, and exchange matter across the galaxy. And for those wondering whether any of this hints at danger, you can let that thought go. Its path never intersects with Earth. Its speed, angle, and distance guarantee a clean pass. Nothing in its motion suggests even the smallest risk. You are watching something extraordinary, not something threatening. What makes this moment remarkable is not peril, but rarity. Not fear, but perspective. Interstellar objects, once thought to be legends, are now turning out to be more common than expected. The universe has always been sending travelers past us. We simply lack the eyes to see them, until now. And as 3I Atlas entered our solar system, NASA's spacecraft began to turn their eyes toward it. When you picture astronomy, you might imagine a single telescope aimed at the night sky. But when an object like 3I Atlas enters the inner solar system, what turns toward it is not one instrument, and not even one planet. It is an entire network stretching across hundreds of millions of miles. You may not feel that when you walk outside at night. The sky looks calm, unchanged. But above you, orbiting worlds you cannot see. With the naked eye, machines built over decades have quietly begun to coordinate, each offering a different piece of a puzzle that scientists are determined to capture before this visitor slips away. The first to react were the orbiters around Mars. Mars Reconnaissance Orbiter, with its high-rise camera, normally focused on dunes, dust devils, and the slopes of ancient riverbeds, was instructed to adjust its schedule. It is rare for HiRISE to devote precious time to something so faint and distant, but the shape of 3I Atlas's tail, even at that early stage, was worth the effort. And so the camera aimed slightly away from its usual terrain, gathering faint signatures that confirmed the comet was already active. Jets releasing gas and dust as the sunlight warmed it for the first time in perhaps 1,000,000 years. Psyche, still in the earliest stages of its mission after launch, was not designed to observe comets. Its imaging system was built for metallic asteroids, not icy visitors. But when navigation cameras are pointed outward instead of downward, they can capture more than their manuals ever described. Engineers rotated Psyche so its cameras could sweep the region where 3I Atlas was expected to appear. The images were faint but usable. Tiny shifts against the star field, movement that helped refine the object's distance through the parallax. Any data is valuable when the subject is this rare. Lucy, on its long arc toward the Trojan asteroids, joined in as well. It was not scheduled to do so. Its instruments had other destinations, other missions, other timelines. But when something from another star enters your neighborhood, missions pause, schedules bend, and cameras make room. Lucy's observations added yet another angle, complementing the view from Mars' orbit. Combined, the spacecraft formed an improvised constellation of watchers, turning their sensors toward the same speck of light from entirely different positions in space. And then came SOHO, the Solar and Heliospheric Observatory, which sits between Earth and the Sun, watching the outer atmosphere of the Sun in almost continuous daylight. During perihelion, when 3I Atlas approached the Sun on October 29th, SOHO became the most important eye in the sky. The expectation was that SOHO would not see the comet at all. The brightness of the Sun tends to wash out faint objects, leaving nothing but glare. But the prediction was wrong. Against expectation, SOHO recorded the comet clearly, its tail stretching behind it as it swept through a region where many comets simply disintegrate. This single moment told scientists that 3I Atlas was stronger than expected. It did not shatter. It did not dim into invisibility. It held its structure through heat and radiation intense enough to strip weaker comets apart. That survival changed every model that followed. It meant December 19th would not be an observation of rubble, but of a still functional interstellar object. As these images arrived, NASA began assembling them in near real time. Parallax from Mars, brightness curves from Lucy, solar imagery from SOHO, and Earth-based telescopes filling in the gaps, all merged into a three-dimensional reconstruction of the comet's shape, its tail, and the tiny fluctuations in its light. These measurements revealed the subtle breathing of its activity. Stronger jets on one side, weaker jets on the other, rotating as sunlight warmed its surface unevenly. To handle situations like this, events too rare and too valuable to treat casually, NASA activates an internal process sometimes referred to as the Interstellar Visitor Protocol. It is not dramatic. It is not secret. It is simply a coordinated set of priorities that shift resources so researchers can capture every available moment. Missions that normally have no connection to one another begin sharing data streams, cameras recalibrate, pointing schedules change. Engineers and scientists meet across departments that usually work on separate projects. It is not a sign of alarm. It is a sign of respect for the science and for the brief chance to study something that comes only once in a generation. And all of this effort carries a simple message for you. Nothing is being hidden. In fact, the opposite is true. When an interstellar object appears, NASA reveals more, not less. The observations increase, the public data releases come faster, and every scrap of information is pushed into the open because the scientific value is too great to hold back. You are watching the result of that openness. Images from half a dozen spacecraft, each one painting the same quiet truth from a different point in space. For many people, the most surprising part was SOHO's success. The spacecraft saw the comet when it was not expected to, and because it saw it, everything we know now becomes clearer. 3I's Atlas survived. It remained active, its tail persisted, and its brightness allowed models to predict its December approach with far more confidence. A network of spacecraft across the solar system turned to watch one visitor. And because of them, the picture you are hearing tonight is steadier, calmer, and far more complete than anything that could have been known even a decade ago. But everything changed on October 29th, the day 3I Atlas reached the sun. When you picture a comet approaching the sun, you might imagine something simple. A glowing head, a trailing tail, a predictable brightening as it draws closer to the heat. But perihelion, the moment a comet comes nearest to the sun, is rarely simple. It is a trial by fire, a crossing into a region so hostile that many comets do not return from it at all. For 3I Atlas, October 29th was that crossing, and every model suggested that this moment would decide whether the object would survive the rest of its journey or dissolve into dust before a single telescope on Earth could capture it again. Perihelion means being pulled into the sun's furnace. Temperatures near the object rose above 1,000 degrees Celsius. Radiation increased by orders of magnitude. Solar tides, differences in gravitational force across the object's surface, stretched at the nucleus the way ocean tides stretch Earth's seas. Many comets break under these conditions. Comet Ison, once predicted to become the comet of the century, disintegrated during its perihelion pass, leaving only a brief streak of debris behind. Its core could not survive the combined stress of heat, radiation, and violent outgassing. That history was fresh in astronomers' minds when plotting 3I Atlas's approach. The object was faint. Its activity before perihelion, though measurable, suggested a potentially fragile structure. And even if it survived, it seemed unlikely that SOHO, the spacecraft watching near the sun, would detect it. The glare should have swallowed it entirely. SOHO has missed brighter objects before. It was reasonable to expect that 3I Atlas would be invisible. But on October 29th, something unexpected happened. SOHO saw it. In the grainy frames of the LASCO instrument, a pale arc appeared, moving along the predicted line. It brightened as it approached the sun. Its tail stretched behind it in perfect alignment with the solar wind, bending and flowing exactly the way physics said it should. And most surprising of all, the object did not flicker as though being torn apart. There were no sudden bursts of brightness, no collapse in its coma, no signs of fragmentation drifting behind it. It held its shape. Against all predictions, the comet survived. This one detail changed the tone of everything that followed. Instead of planning for a cloud of debris, astronomers realized they would be studying a still intact interstellar visitor as it moved back into view. The survival of 3I Atlas meant its internal structure was stronger than many expected. Perhaps its ices were more tightly bound. Perhaps its dust was packed differently. Perhaps the conditions where it formed were colder, older, or denser than anything in our own system. NASA began analyzing the data immediately. The first measurements focused on its brightness, how quickly it intensified near perihelion, how sharply it dimmed after passing the sun. These brightness curves reveal how much gas and dust a comet releases, and 3I Atlas showed a controlled, steady response rather than the chaotic flare-ups that precede collapse. Then came measurements of jets, the narrow streams of gas erupting from the surface. Their strength increased, as expected near perihelion, but never reached destructive levels. And the coma, the glowing envelope surrounding the nucleus, expanded slightly and then stabilized, never ballooning into the unstable shape that suggests internal cracking. All these details pointed to the same conclusion. 3I Atlas was not behaving like a fragile comet from our own system. It was behaving like something tougher, something that had weathered conditions we do not fully understand. Its composition may include ices we rarely see here, or mixtures of dust and frozen gases that hold together differently. This was not only scientifically interesting, it was deeply unexpected. For a moment, the astronomical community held its breath. Perihelion had passed. The object had survived the worst. And as the glowing dot moved away from the sun, there was an almost collective exhale from observers around the world. They had been granted something extremely rare: the chance to study an interstellar comet both before and after its closest encounter with the sun. Matthew Knight, one of the leading comet researchers, once said, "Perihelion is where comets show what they're truly made of." On that October day, 3I Atlas showed that it was made of something resilient, something shaped by a different kind of winter, somewhere far beyond our understanding. Yet even as scientists prepared their next round of observations, lining up telescopes, recalculating brightness models, waiting for the object to reappear, another surprise was waiting. A few days after perihelion, as Earth rotated beneath quiet November skies, telescopes searched for the comet's return and found nothing. The object that survived the sun had slipped out of view completely. And just when astronomers prepared for the next round of observations, the comet vanished. When a comet disappears, most people imagine something dramatic: a breakup, an impact, a sudden failure of instruments. But in astronomy, disappearance often has a far simpler explanation, one that has nothing to do with danger or secrecy, and everything to do with geometry. Specifically, with the moment when an object drifts too close to the line of sight between you and the sun. This moment is called solar conjunction, and for 3I Atlas, it arrived only days after its survival at perihelion. Solar conjunction happens when a planet, spacecraft, or comet passes near the sun from our perspective on Earth. The object isn't gone. It isn't hidden. It's just overwhelmed by sunlight, drowned in brightness so intense that no telescope can distinguish it from the glare. The instruments become effectively blind, not because they malfunction, but because the sun is simply too bright for anything smaller to stand out. You've seen versions of this before, even if you didn't realize it. Venus routinely slips behind the sun and vanishes for weeks, only to reappear exactly where orbital calculations say it should. Mercury disappears so often that its cycles are mapped out years in advance. Even Mars experiences this blackout. During its conjunction, NASA stops sending commands to its rovers entirely because solar interference can scramble signals mid-transmission. If planets can vanish without mystery, it's not surprising that a faint interstellar comet would as well. But for many people following 3I Atlas online, the disappearance felt different. It happened right after perihelion. Right after excitement surged from the images showing its unexpected survival. And when amateur astronomers couldn't locate it in the nights that followed, speculation spread quickly. Some wondered whether it had fragmented. Others suggested it might have shifted course. A few claimed NASA was withholding information, or that unusual silence meant something had gone wrong. The truth was far quieter, far simpler, and far less dramatic. Astronomers knew exactly where the comet was. Even without direct images, its motion could be calculated with extraordinary precision. When you know an object's speed, angle, and distance, you can predict its position, even when it slips behind the sun. That calculation is routine work, the same mathematics that tells us where Jupiter will be next month and when an eclipse will occur 50 years from now. Everything was exactly where the math said it would be. Nothing about 3I Atlas's behavior suggested danger or deviation. It followed the predicted arc. It dimmed exactly as expected after the furnace of perihelion. Its distance increased on schedule. The only thing that changed was our ability to see it, a temporary, inevitable consequence of its alignment with the sun. NASA Jet Propulsion Laboratory summarized this in a single clear sentence. Solar conjunction is a blackout by geometry, not by secrecy. Still, for people watching from afar, the disappearance created a vacuum, a pause in information that social media filled instantly. The human mind dislikes empty spaces. When updates stop, imaginations take over, sometimes gently, sometimes chaotically. And in the absence of new images, theories began to multiply. A few were thoughtful, many were not, but all of them came from the same fundamental truth. People were paying attention. People cared. If anything, the disappearance proved how unusual this moment is. Most comets pass unnoticed. Most fade in and out of view, without a ripple of public interest. But a visitor from another star, approaching closer than any before, watching its tail twist and its brightness fluctuate, that captures attention in a way few astronomical events do. Solar conjunction amplified that attention. It turned a normal blackout into a moment of worldwide curiosity. It created tension, the quiet kind you feel when a story pauses just before something important happens. And in its own way, it helped prepare people for the next chapter, because what matters is not the blackout itself, but what comes after. And what came after was not expected. When the comet returned to view, it did not look the same. Its brightness was different. Its shape had shifted. The features that scientists studied before perihelion no longer matched the ones they saw after. This was not evidence of danger. It was evidence of change. Normal for comets, fascinating for scientists, and especially intriguing when the comet in question comes from another sun. This is why solar conjunction matters. It marks the pause between two versions of the same object. Before the blackout, 3I Atlas was defined by its approach: heating, brightening, outgassing, revealing its outer layers for the first time in ages. After the blackout, it would be defined by its retreat: cooling, settling, shedding a new pattern of dust shaped by what it experienced near the sun. And so, as the days passed and conjunction reached its end, telescopes around the world waited for the comet's reappearance, not with fear, but with curiosity. They knew the object would return on the exact day calculations predicted. They knew what patch of sky to watch. The only question was how it would look when it stepped out from the sun's glare. And then, right on schedule, 3I Atlas reappeared, changed. When 3I Atlas finally emerged from behind the sun in mid-November, the moment felt almost like watching someone step out from behind a curtain after being gone longer than expected. You knew exactly where it would appear. Every calculation pointed to the same coordinates. But knowing the location and seeing it again with your own instruments are two very different things. And when the faint shape resolved back into view, astronomers immediately understood that this was not the same comet they had watched before conjunction. It had returned, yes, but it had returned changed. The first sign was its brightness. Before perihelion, the comet followed a predictable curve, gradual brightening, a small dip, then a sharp rise as it approached the sun. After conjunction, the brightness was lower than expected. Not drastically, just enough to suggest that the comet had shed a thin layer of volatile material during its closest pass. This is entirely normal. After all, it had faced temperatures over 1,000 degrees and radiation strong enough to vaporize metals. Most comets lose more than this, but the change was noticeable, and it set the tone for everything that followed. Then came the tail. Before perihelion, 3I Atlas carried a broad, wide dust tail that stretched behind it in a stable arc. After reappearing, the tail was narrower, more defined, and angled differently than before. The solar wind had shifted in the weeks of conjunction, altering the direction in which dust and ions were swept away. Think of it like a breeze, changing direction around a campfire. The smoke is still smoke, but its shape and flow transform instantly. The coma, the cloud of gas that surrounds the nucleus, had changed as well. It had shrunk slightly, becoming more compact and more sharply defined. This happens when the heating from the sun decreases. As the comet moves outward, its surface cools, jets weaken, and the envelope of dust and gas becomes tighter around the nucleus. Far from being a sign of distress, this contraction is a natural response to the comet's changing environment. But the detail that caught everyone's attention was something stranger: the appearance of what looked like an anti-tail. For a casual observer, it might appear as though the comet had grown a second tail pointing in the opposite direction. Social media lit up within hours. Images from amateur astronomers matched the early professional exposures, and the same thin, straight streak appeared in both. Some thought it was a sign of fragmentation. Others assumed it meant a sudden shift in outgassing. But an anti-tail is not a second tail at all. It is an illusion of geometry. When a comet passes through the plane of the solar system, dust that lingers behind it can line up almost exactly with Earth's line of sight. From this angle, instead of fanning outward like a typical tail, the dust seems to form a straight spike pointing toward the sun. It looks impossible, but it's actually one of the oldest documented comet phenomena. And for 3I Atlas, the effect was unusually strong, suggesting that the dust distribution behind the comet was finely layered. To astronomers, this was not a sign of danger. It was a gift, a rare chance to study the three-dimensional structure of interstellar dust grains. The ESA astronomer who first commented on the new images said it best: "Comets don't return unchanged. The sun always leaves its signature." For 3I Atlas, that signature came in the form of subtle shifts: dust redistributed by solar wind, a coma shaped by cooling gases, and a tail that told a story not of instability, but of angles, motion, and perspective. Spectroscopy added even more clarity. Measurements taken across several nights showed that the ratio of CO to CO2 had decreased, exactly what you would expect after a close approach to the sun. Water vapor output had weakened too. These changes confirmed that the comet's activity level was now settling into its post-perihelion behavior. Nothing in the data suggested breakage or collapse. Instead, the numbers painted a picture of a resilient object responding naturally to its environment. And behind all of this was something deeper, a lesson about interstellar visitors themselves. Most long-period comets in our solar system follow similar patterns because they formed under similar conditions. But 3I Atlas was made somewhere else, somewhere colder, darker, and far more ancient. Its ices have different strengths. Its dust grains have different structures. Its outgassing behaves in ways that offer scientists rare opportunities to compare the chemistry of our solar system to that of another. None of these changes were signs of danger. They were signs of difference. For you, listening now, the meaning is simple but profound. The comet's reappearance is not a warning. It is an invitation to see how objects from other stars evolve, shift, and settle as they pass through the warmth of our sun. And for astronomers, these changes carry practical importance. They allow models to predict how the comet will behave during its closest approach on December 19th. They refine estimates of brightness. They sharpen expectations about tail length, coma structure, and visibility. What you are seeing now, in mid-November, is the comet learning to breathe again after its encounter with the sun. It is cooling. It is shedding old dust. It is revealing a different form, a form shaped by the forces it endured, and that form will shape everything that happens next. To understand what December 19th will reveal, you need to look deeper into the structure of the comet itself. When you look at a comet through a telescope, you see only light, soft, hazy, distant. But inside that light is a story written in chemistry, a story that astronomers read using a technique older than spaceflight and more delicate than photography. It's called spectroscopy, the process of separating light into its colors, revealing the fingerprints of the molecules that created it. Every chemical emits and absorbs light at slightly different wavelengths. Spread the comet's glow into a spectrum, and suddenly you are no longer looking at a blur. You are looking at its ingredients. For 3I Atlas, that spectrum tells a quiet but astonishing tale. The first molecules revealed were familiar ones: water ice, carbon monoxide, carbon dioxide, and traces of methanol, CH3OH, along with a population of microscopic dust grains. These are the same building blocks found in many comets within our own solar system. But the secret is not just what is present, it's how much of each ingredient appears, and what those proportions imply about the world this object once called home. The ratios of CO to CO2, the strength of the water signature, and the presence of certain organic compounds all point to formation temperatures lower than those found in the Kuiper Belt, the distant ring of icy bodies beyond Neptune. That means 3I Atlas likely emerged in a region colder than anything near our sun. Much colder. Colder even than the environments that formed long-period comets like Hale-Bopp. It hints at a cradle, for from its parent star, in a zone where gases freeze into solids that would vaporize instantly closer in. Its chemistry suggests it formed in conditions colder than any region of our own solar system. Data from Psyche and Lucy, the spacecraft that captured faint readings during their improvised observations, added another layer to the picture. The dust around 3I Atlas appears to have lower density than expected, but not because it is fragile. Instead, the dust grains are compact, tightly bound, with fewer voids than many comets here. Some comets in our system are almost fluffy, like cosmic snowballs built from loosely packed ice crystals. But this one seems different, as though its materials were compressed slowly over immense spans of time, preserved in deep cold until the moment sunlight finally touched them. When you compare the activity of 3I Atlas to that of Comet Borisov, the second known interstellar visitor, the differences grow even more interesting. Borisov was extraordinarily active, releasing dust rapidly and forming a broad, diffuse tail. It brightened quickly, but also shed mass at a pace that suggested it had little structural strength. 3I Atlas, on the other hand, releases gas and dust more steadily. Its activity is sustained rather than explosive. And its ion tail, the narrow, glowing streak created when solar radiation strips electrons from gas molecules, is cleaner, straighter, and stronger than Borisov's ever was. This is part of what excites astronomers so deeply. These objects are both interstellar, yet they are not alike. Each carries traces of a different system, a different sun, a different history. As Avi Loeb once said, every interstellar object carries a chemical memory of its home system. And tonight, as you hear these details, you are witnessing a memory from a place humanity has never seen. Understanding the composition of 3I Atlas matters for reasons that go beyond curiosity. It tells astronomers how bright the comet might appear during its closest approach on December 19th. Will it be within reach of backyard telescopes? Will its tail lengthen? Will the coma expand again? The answers lie in the chemistry. How volatile its ices are, how they respond to sunlight, how quickly they release dust as the object cools and warms along its path. The composition also determines how long certain features persist. A comet rich in CO brightens sharply, but fades just as quickly. A comet dominated by water ice tends to respond more gently. And a comet with a mix of both, especially one that formed under conditions far colder than our solar system ever experienced, may follow patterns still unfamiliar to us. That is why this part of the story feels so quietly profound. You are not just learning what the comet is made of. You are learning where it has been. You are learning about a world beyond your world, its climate, its chemistry, its ancient winter that lasted longer than all of human history combined. Everything we know about 3I Atlas today comes from photons that left its surface hours ago, traveled silently through space, and then struck a detector on Earth or a spacecraft orbiting another planet. In those photons is information from a system so remote that no spacecraft will ever reach it. There is something deeply calming in that realization. While life here moves quickly, while days blur, while obligations stack, while uncertainty rises and falls, the universe writes its stories slowly. A comet carries its history not in language, but in ratios of frozen gases, in layers of dust, in the glow that spreads across a sensor when the right instrument is pointed upward at the right time. And in those patterns, astronomers find the clues they need to continue the journey through this story. Clues that will help reveal what 3I Atlas will look like when it sweeps past Earth on December 19th. Now that we know what it's made of, we can finally ask the next question. How is it moving? When you hear people online talking about the comet changing direction or speeding up, it can sound unsettling. Space, after all, feels like a place where objects should follow perfect, predictable lines. But the truth is simpler, calmer, and far more elegant than the rumors suggest. The path of 3I Atlas is not only predictable, it is one of the most predictable kinds of paths in celestial mechanics, a hyperbolic orbit. A hyperbolic orbit is a shape of departure. It is not a loop or circle, not an elongated oval that promises to return centuries later. It is an open curve, wide and smooth, indicating that the object is not bound to the sun at all. The sun's gravity pulls on it, yes, but cannot keep it. 3I Atlas arrived with too much speed, too much momentum gathered across the cold distances between stars. It will sweep in, bend gently around the sun, and then continue outward forever. That shape alone is enough to tell you that it poses no threat. A comet on a path like this cannot suddenly decide to bend toward Earth. It has no physical mechanism that allows for that kind of behavior. Still, the comet's motion is not entirely untouched by other forces. Like all small bodies, 3I Atlas is steered by a combination of gravity and much weaker influences. The Sun's gravity is the dominant one, shaping the vast curve of its journey. The large planets tug lightly at it, though their effect is tiny at such distances. More interesting is solar radiation pressure, sunlight itself pushing on the dust streaming from the comet, nudging it by small, steady amounts. And finally, there is outgassing, the process of jets of gas erupting from the nucleus as sunlight warms certain patches of ice. These jets act like minuscule thrusters, creating gentle but measurable changes in the comet's motion over time. It is these jets, not danger, that cause the small trajectory updates people see in NASA's daily reports. They are not corrections. They are refinements, adjustments to the model as new information arrives. A jet can exert a force smaller than a household hairdryer, yet over months, that tiny push can shift a comet by hundreds of kilometers. Not enough to change its overall path, not enough to alter its distance from Earth by any meaningful amount, but enough that astronomers who work in the language of precision mark the change. NASA updates its model every night because new data arrives every night. Changes in brightness, updated detections from Earth-based telescopes, parallax measurements from Mars orbiters, and faint detections from spacecraft like Psyche that see the comet from different angles. Observing a body from multiple positions in the solar system reduces uncertainty. The comet isn't wandering. Our view of it simply becomes sharper. Think of it as focusing a camera lens. The subject stays in place while the picture gets clearer. One of the most reassuring details is the distance. Even at its closest, on December 19th, 3I SOHO Atlas will remain more than 10 million kilometers from Earth, over 25 times the distance to the Moon. Imagine an arrow aimed at a target on the far horizon. Now, imagine that the arrow's path might shift by the width of a grain of sand. That is the scale we're talking about when people worry about trajectory changes. The small variations do not alter the overall direction. They fit perfectly within what physics predicts. So, why do rumors spread? Part of it comes from misunderstanding the terminology. When NASA publishes an updated orbit, some people interpret that as evidence that the comet has done something unexpected. But those updates are simply the result of better data. Brighter images, clearer tail structures, improved distance measurements. As Paul Chodas of the Center for Near-Earth Object Studies explains, non-gravitational forces are expected. They are not anomalies, they are data. Another source of concern is the subtle language of orbital mechanics. Words like correction, update, or refinement can sound alarming if you don't work with them every day. In reality, they're routine. Astronomers refined the orbit of Halley's Comet for centuries. They adjust the paths of near-Earth asteroids whenever new observations come in. They revise predictions for planets, moons, and spacecraft for the same reasons. It means the system is working exactly as it should. For 3I Atlas, the refined data from Mars orbiters and Psyche has been especially valuable. These spacecraft, positioned far from Earth, provide a second viewpoint, an effect known as parallax. With two viewpoints, astronomers can triangulate the comet's position with far greater accuracy, reducing uncertainties from thousands of kilometers to mere hundreds. And when you are measuring something 10 million kilometers away, That level of precision is extraordinary. The most important truth in all of this is that nothing about 3I Atlas's motion suggests risk, not its speed, not its angle, not its drift. Everything about its path matches exactly what an interstellar comet should do when passing close to a star, and nothing about its behavior indicates any deviation that could bring it nearer to Earth. Nothing about its motion indicates danger. Everything about it indicates opportunity. Opportunity to study something ancient, something that formed under another sun, something that will never pass this way again. Understanding its orbit helps you understand why December 19th is not a day to fear, but a day to observe, a day to appreciate the rare alignment that allows humanity to witness a traveler from the cold between stars. But trajectory is only half the story. The other half is what astronomers are actually seeing every night. If you stepped outside tonight and looked up, you might not see anything unusual. The sky looks unchanged, indifferent, the same quiet dome of stars you've known for decades. But behind that quiet scene is an extraordinary level of activity, an entire planet's worth of telescopes, both professional and amateur, turning toward a single, faint visitor drifting through the darkness. For the first time in history, an interstellar object is being observed not just by scientists in isolated observatories, but by a global community watching together. NASA is, of course, at the center of this effort. Their telescopes, from ground-based facilities to orbiting spacecraft, are gathering every photon they can. ESA's network joins in from the other side of the Atlantic. Observatories in Chile and South Africa have opened their domes night after night, taking advantage of their crystal-clear skies. And beyond these major institutions, countless smaller telescopes, robotic systems, university observatories, backyard installations, are all pointed at the same moving blur. What makes this moment remarkable is not just the number of telescopes, but the diversity of the people behind them. Some are professionals with decades of experience. Some are retirees with 8-inch telescopes mounted in their yards. Some are teenagers running robotic telescopes remotely from their laptops. They're all looking at the same thing, a wedge of faint light stretching through the cold sky. To capture that light, observers use techniques designed to draw detail out of faint objects. Long exposure stacking, multiple images combined into one, reveals the comet's delicate tail structure. Narrowband filters isolate specific gases, allowing scientists to map how the comet's chemistry changes night to night. Spectroscopy breaks the glow into wavelengths, the same technique that revealed its chemical makeup earlier. Some astronomers even image through moonlight, timing their exposures to minimize glare. And then there are the amateur images, an unexpected treasure. Some of the best images of 3I Atlas were taken in backyards, not observatories. With sensitive modern cameras, long patience, and clear winter skies, amateurs produce data that sometimes rivals semi-professional imaging. What they lack in aperture, they make up for in numbers. For every one observatory image, there might be 100 amateur ones. This sheer volume fills gaps professional telescopes cannot cover. Patches of sky lost to clouds, hours missed during instrument calibration, moments when a small telescope happens to be perfectly aligned. But observing the comet is not simple. Its brightness remains low, requiring careful techniques to detect. The moon's phase can wash out the faint tail. Weather interferes unpredictably, and the comet's position near the horizon in some regions makes imaging particularly challenging, forcing observers to work during narrow windows each night. NASA understands how valuable this data is, and they have issued what they call rapid follow-up requests. This is not common. It means telescopes are asked to observe quickly whenever new information arrives. An outburst, a brightness change, or a tail shift. This urgency has caused several observatories to rearrange their schedules, deviating from planned targets because interstellar visitors are too rare to ignore. You do not get many chances to study something that has traveled for millions of years to reach your sky. From all these perspectives, Chile, South Africa, Europe, the Americas, orbiters beyond Earth, scientists assemble a three-dimensional reconstruction of the comet's tail. Dust grains drift in arcs. Ion particles stretch in straight, rigid filaments. The shape evolves as the comet cools and rotates. Observing from multiple angles allows astronomers to separate what is real from what is merely viewing geometry. Without these combined observations, the complexity of its structure would be impossible to understand. This global attention is not driven by fear. It is driven by rarity. Even Oumuamua and Borisov, the only two interstellar visitors confirmed before this, never received this depth of coverage. They were too fast, too fleeting, too distant. 3I Char Atlas moves slower, passes closer, and stays visible longer. It is the first interstellar object that humanity can truly study from all sides. And it is the first interstellar object that everyday people can watch unfold almost in real time. There is something deeply human in that. Someone in Arizona, with a simple mount and a cooled camera, can photograph the same object as a billion-dollar observatory in the Atacama Desert. Someone in Italy can live stream their capture to thousands of viewers who will never look through a telescope themselves. Gianluca Massi of the Virtual Telescope Project once said, "Astronomy becomes meaningful when people feel included in the discovery, and right now, the world is included." But the opportunity will not last. The comet is approaching a brief observing window, a one-time slice of days when the angle, distance, and brightness all align just right. Early December marks the beginning of this window. The 18th and 19th are the peak. After that, the comet will fade, slipping back into the darkness. Within a few weeks, it will be beyond the reach of most telescopes. A few weeks more, and only large facilities will be able to find it. By early next year, it will disappear from observation entirely. That is why this moment matters. That is why so many telescopes are pointed toward the same faint streak. This is the only time you will ever see 3I Atlas. The only time the world will observe it together. The only time its light will pass through Earth's sky. So what, exactly, will all these telescopes see on December 19th? After everything you've heard, the journey from another star, the perihelion, the disappearance behind the sun, the return with new features, your mind eventually lands on the question everyone asks first. What will actually happen on December 19th? Not the rumors, not the speculation, the truth. December 19th is the moment when 3I Atlas passes closest to Earth. Closest, though, is a relative term. The comet will still be millions of kilometers away, more than safe, more than comfortable, more than completely harmless. At that distance, it cannot influence Earth's gravity. It cannot affect satellites. It cannot disturb magnetic fields, weather systems, or anything else in our environment. It will glide past our world the same way a distant airplane crosses the horizon. Visible only to those watching for it, and entirely indifferent to what lies below. What you will notice, if you know where to look, is a faint, compact glow. Astronomers estimate that on December 19th, 3I Atlas will reach magnitude 8 to 10, depending on its activity level. That means your eyes won't see it, even under perfect dark skies, but a camera will. A simple 10 to 20 second exposure on a consumer astrophotography setup will reveal a small, tight coma surrounded by a whisper of light stretched into a tail. By that date, its coma is expected to be smaller and more condensed than it was at perihelion. These objects always quiet down as they move away from the sun. But the ion tail, driven by solar radiation, not by the comet's own heating, may be long, slim, and surprisingly clean. Under the right angle, an anti-tail may appear again. That strange geometric effect when dust aligns with Earth's perspective. Not guaranteed, but possible. A small visual reward for those who stay curious. December 19th will also be the comet's fastest apparent motion relative to Earth. Not dangerous speed, just visually striking speed. In a single hour, the comet will shift enough that astrophotographers will have to adjust their tracking. For most celestial objects, the sky feels frozen. For this one night, the motion becomes something you can detect on camera frames taken minutes apart. It is a reminder that the comet is not part of our system. It is passing through, not belonging here, moving to a rhythm set far beyond our sun's authority. NASA and observatories worldwide will be collecting the most detailed measurements of the entire event on that day. Spectrographs will study the balance of gases in the coma: water, CO, CO2, trace organics, and compare it to earlier measurements. Telescopes will assess the activity level, how much dust is escaping, how strong the jets are, how the balance shifts at this distance. And of course, there will be precise orbital measurements. December 19th offers a clean geometry, allowing astronomers to measure the comet's trajectory with exceptional accuracy, locking in the final model before it fades into the dark. But it's equally important to say what won't happen on December 19th. It won't collide with Earth. It won't disturb the climate. It won't shake the magnetosphere. It won't change Earth's rotation, cause tides, or interfere with satellites. And it cannot, in any physical sense, affect human life. The rumors circulating in certain corners online, gravity spikes, radiation surges, mysterious energy interactions, have no foundation in physics. Nothing dangerous, everything meaningful. Because what actually happens on December 19th is not a threat, it's a privilege. Humanity will witness the closest interstellar object passage ever recorded. A piece of a distant sun system will glide just above our cosmic doorstep. Scientists will gather data that may not be possible again in your lifetime. Amateur observers will point their cameras at a memory from another star. And people all over the world, some on rooftops, some watching live streams, some only listening to stories like this one, will know that an object older than our world is sweeping past them in silence. The scientific value is enormous. These observations will help refine models for comet formation in alien systems, models we barely had before Oumuamua and Borisov appeared, and models we are rewriting now with each new measurement from 3I Atlas. Astronomers will compare its dust and gas to earlier interstellar visitors, trying to understand whether these objects represent typical samples of foreign planetary systems or rare survivors expelled during violent eras of star formation. Every spectrum, every image, every angle adds to that story. But beyond science, there is the quieter meaning. Standing on your porch, the night of December 19th, even if the sky is cloudy, even if you can't see anything, you can take a moment to remember that above you, just beyond visibility, is matter from another star passing through your sky. It is not science fiction. It is not imagination. It is real, moving across the night like a messenger from a place you will never visit. NASA summarized it best. This is not an event of danger. It's an event of opportunity. And that opportunity is not just scientific. It is personal. But to truly understand why this moment matters, we need to zoom out to the scale of the galaxy. When you think about the solar system, it's easy to imagine it as a kind of sealed container, a sphere of planets, moons, and comets orbiting the sun in endless loops, isolated, self-contained, untouched by anything beyond its borders. For most of your life, that idea has felt natural. The planets stay in their lanes. The stars stay impossibly far away. Space feels like a series of separate rooms with locked doors. But the truth is softer, blurrier, and far more connected than that. The solar system does not have a sharp edge. There is no wall where sunlight stops and interstellar space begins. Instead, there is a vast faint boundary, a fuzzy transition zone stretching trillions of miles outward. This is the realm of the Oort cloud, a sphere of icy bodies so distant that the sun is only a bright star there. In this outer region, gravity is gentle. The pull of distant stars becomes noticeable, and even small disturbances can nudge objects across the dark. Over millions of years, passing stars drift close enough to tug that cloud, stirring its contents. Sometimes, those nudges send fragments inward toward the sun as long-period comets. Sometimes, they send material outward, away from our system entirely, letting it drift into the galaxy as wandering debris. And the same thing happens in other star systems. Dust, ice, rock, and organic molecules are constantly being shaken loose, expelled, exchanged, shared. Our solar system is not walled off at all. It is porous. In that context, 3I Atlas is not an intruder. It is a traveler, a piece of another star's history that has drifted through the galaxy long enough to find its way here. Its composition carries what scientists call a chemical memory, a frozen record of the temperature, pressure, and ingredients of the place where it formed. When it passes through our system, it brings with it information that no telescope alone could ever reveal, because it is not just light from a distant star, but matter from it. Interstellar objects like 3I Atlas tell us how planets form in places we will never visit. They tell us how ice behaves in temperatures far below anything found near our sun. They help reveal how dust clumps together, how organics survive cosmic radiation, how volatile gases freeze and thaw in alien environments. Every interstellar visitor is a tiny probe launched by physics itself. No fuel, no mission design, just time and motion. And they hint at something even larger. If material from another star can reach us, then material from our star can reach others. The galaxy is not quiet. It is a place of constant exchange. Avi Loeb expressed it clearly. The galaxy is not quiet. It is a place of constant exchange. You live inside a cosmic neighborhood where matter drifts freely, nudged by the gravity of stars that were born long before Earth existed. The things that form comets here, the ices, the dust, the organic precursors, are the same things forming comets in faraway systems. Every system contributes something. Every system receives something. This flow has potential biological implications too. Speculative, yes, but worth considering. If simple organic building blocks can travel between systems, then the seeds of chemistry might be shared across the galaxy. Not life itself, but the ingredients of life. Panspermia, not as a claim, but as a possibility. The thought alone is enough to widen your sense of where we belong. And beneath this scientific meaning lies something more emotional. The reminder that we are not isolated. Earth orbits the sun. The sun drifts around the Milky Way. And in that 4 billion mile per hour journey, our system grazes regions influenced by ancient stars, future stars, and stars that have already died. We live in a galaxy where stars share material like distant neighbors, rarely meeting, but always affecting one another through the physics of space. Interstellar visitors may have passed through our solar system for billions of years, long before humans existed, long before dinosaurs, long before Earth had continents. Every so often, one passes close enough for us to see it, and in those moments, we glimpse the larger pattern. Our system is part of a moving, interacting, living galaxy. 3I Atlas is one of those moments. Not a warning, not a disruption. A reminder. A reminder that you are standing on a small world inside a larger community of stars. A reminder that the materials that built Earth did not form in isolation. A reminder that the galaxy is not empty. It is busy, exchanging matter, energy, dust, and fragments of ancient sunlight. And in that flow of cosmic migration, you are watching a traveler pass by. But beyond the science, the question becomes personal. What does this moment mean for you? When the night of December 19th arrives, you might step outside for only a moment. Maybe the air will be cold. Maybe the sky will be quiet. Maybe you'll look up for just a few seconds before heading back inside. But in that short moment, something remarkable will be happening above you. Something you may never witness again. You will be standing beneath an object made of material from another star. Not starlight, not radiation, not a signal traveling at the speed of light. Actual material, ice, dust, and ancient molecules that condensed around a sun you will never see in a region colder than any corner of our solar system. Carried across interstellar space for millions of years, and somehow, through the quiet coordination of gravity and time, it happens to cross Earth's sky while you are alive to notice it. You are living at the exact moment when a visitor from another star drifts past your world. That alone makes this moment personal, not scientific, not dramatic, but deeply human. Very few generations have ever witnessed an interstellar object. For most of human history, no one even knew they existed. Your lifetime has seen Oumuamua, Borisov, and now 3I Atlas. Out of the hundreds of billions of people who will ever live, you are among the tiny fraction alive during a time when humanity can detect, track, and understand objects that do not belong to our solar system. You are not just hearing a story about it. You are here while it is happening, while the comet is moving above your horizon, while telescopes are capturing its details, while its tail stretches across the dark. You are a witness to something rare at a time when witnessing is possible. And that is meaningful in a way that numbers cannot explain, because standing under a sky with an interstellar visitor does something subtle to you. It loosens the tight focus of your daily world. It softens the edges of things you've been carrying all day. Deadlines, expectations, conversations, worries. It gives you perspective without demanding anything from you. You don't need to study astronomy to feel that shift. You just need to pause long enough to sense that you are part of something larger than your routine. The comet will not change your life in a physical sense, but it might change how you look at your life. For a moment, the world becomes bigger. Your problems become smaller. Your thoughts slow down. You feel a kind of spaciousness inside you, the kind that comes from realizing that your life is unfolding inside a galaxy that has been exchanging matter for billions of years. Your breath steadies, your shoulders drop. You understand, without needing words, that you are woven into something ancient and vast. Time takes on a different meaning too. 3i Atlas started this journey long before the first humans walked the Earth, long before our continents took shape, long before our sun had completed a single orbit around the Milky Way. And yet, after millions of years traveling through the deep cold, after drifting past distant stars and slipping through unseen gravitational tides, it arrives here now, on a night when you happen to be alive, awake, and listening. You only need 30 seconds to look up at the sky, to understand that your own life is part of a much longer story, a story that stretches far beyond a single lifetime, far beyond the boundaries of human history. There's also a sense of community woven into this moment. On December 19th, millions of people across Earth will be looking toward the same small region of the sky. Scientists, amateurs, families, and quiet watchers like you. A rare moment of shared curiosity where humanity pauses, not out of fear, not out of urgency, but simply to witness something beautiful and strange. You become part of that shared moment, part of that thin thread of connection stretching across continents and oceans. And then there's the deeper question, the one that hums softly beneath all of this. Where did these molecules come from? What star formed them? What chemistry shaped them? How many systems did this object pass us near before reaching ours? Could the organic compounds in its dust have once been the raw materials for life elsewhere? No bold claims, no conclusions, just the gentle curiosity that arises when you realize the universe may be more connected than it seems. Carl Sagan captured this feeling long ago when he said, "We are a way for the cosmos to know itself." Tonight, as you lean back for a moment and let your mind soften into that idea, you become part of that knowing. You become part of the quiet awareness the universe has of its own motion, its own history, its own endless weaving of light and matter. And that is why this moment matters. Not because it will change the world, but because it might change how the world feels. Even just for a night, it might remind you that you are small, yes, but not insignificant. That you are temporary, yes, but not disconnected. That you are here, alive, at the same time a traveler from another sun crosses above your sky. And when the night of December 19th fades, the comet will begin its slow journey outward, away from us. After December 19th, the story of 3i Atlas does not end abruptly. It simply continues in a quieter direction, away from us, away from the warmth of the inner solar system, back toward the long night it came from. The brightness that once made astronomers lean a little closer to their screens will begin to slip. Each night, it will fade a little more. The coma that once glowed like a soft lantern will loosen, thinning until it becomes almost indistinguishable from the background of distant stars. And the ion tail, sharp, narrow, clean, will stretch out into nothingness as the solar wind weakens its grip. You might imagine this moment like watching someone walk down a long hallway, their silhouette shrinking step by step, until eventually the darkness swallows the last outline. That is what will happen in the sky. Over days, then weeks, the comet will sink deeper into the quiet, until only large observatories can still find it. And then, eventually, even those observatories will let go. After its closest approach, 3i Atlas will continue outward, crossing the orbital distance of Mars as winter deepens here on Earth. Mars will not notice, of course. The comet will be far away, just a faint traveler moving through the emptiness between planets. Months later, it will drift beyond Jupiter's orbit, slipping into regions where sunlight grows thin, and only the cold remains. The sun's gravity will weaken with every million kilometers gained, and sooner than you might expect, the comet will reach a point where the sun no longer holds it in any meaningful way. In that moment, 3I Atlas becomes what it has always been, a wanderer without a tether. A year or two after December 2025, it will vanish entirely from our instruments. Not because anything dramatic happens. It will not break apart, or flare, or send a visible signal of departure. It will simply become too faint. The dust surrounding it will settle. The ices will quiet. Its light will spread too thinly across space for even the best detectors to gather it. It will return to the state it was in for millions of years before we discovered it. Unseen, unmeasured, unknown. And after that, its future belongs to the galaxy. It may pass near another star system, tens of millions of years from now. It may be nudged by a gravitational tide. It may collide with a grain of dust or a fragment of rock drifting in the void. It may break apart in a place no one will ever witness. Or it may continue intact, moving through the dark like a sealed envelope carrying the chemistry of its birthplace. But for us, for Earth, its story ends here, in December 2025. There is no sadness in this ending, only completeness. A comet is not a friend we lose, or a light that dims because something went wrong. It is a visitor, and every visit has a natural end. Its departure honors the same physics that brought it to us in the first place, the same long, slow drift, the same quiet choreography of gravity and time, the same vastness that makes the galaxy a place where encounters like this are rare and meaningful. Imagine it as a guest quietly stepping out into the night after leaving something behind, an impression, a memory, a reminder that the universe is larger than we often let ourselves remember. It doesn't wave. It doesn't linger. It simply continues its path, carrying secrets from a star we've never seen. This is the last time in your life you will hear its name in the night sky. Not because the story ends, but because our chapter ends. And there is something deeply peaceful about that, like turning the final page of a book you loved, one that didn't need a dramatic conclusion, because the journey itself was the point. The comet arrived, revealed itself, survived the sun, returned changed, and then drifted away exactly as the laws of nature intended. Once it fades from our telescopes, it will never return. This is a farewell, not a sad farewell, but a gentle one. A closing of a door that was always meant to close. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." And yet, moments like this somehow do. A visitor from a distant star comes near, shows us something rare, and moves on. It doesn't explain itself. It doesn't stay long. But it leaves us with perspective. And maybe that is the only sense we truly need. And as it drifts into the silence, let's take a moment to breathe and return to ourselves. Tonight, as you settle into the quiet of your room, the long story you've just followed begins to fold itself gently closed. You've traveled with an object that did not begin its journey anywhere near here. It came from between the stars, crossed the deep cold of interstellar space, slipped into our solar system, and drifted toward the sun. You followed it through its closest brush with our star, through the moment when it vanished into the glare, through its quiet reappearance after conjunction. You watched it grow brighter, then softer, then pass by Earth at its closest distance, and finally begin its slow retreat back into the dark. It arrived. It showed itself. And now it's leaving again. Nothing about its presence threatened Earth. Nothing about its motion hinted at danger. Your world stayed the same. You still woke up in the morning, made coffee, answered messages, navigated your day. And tomorrow, you will do those things again. But something subtle has shifted. Not in the world, but in the way you feel your place in it. You've spent more than an hour with a story that reaches outside the boundaries of the everyday and gently widens the space inside your thoughts. That widening is part of the gift. Because now, as the last traces of 3i Atlas drift away, you can begin returning to yourself. Not abruptly, not with noise, but with the same softness the comet showed as it faded. You are still the same person who works, who worries, who deals with unexpected things. You still have responsibilities waiting for you when morning comes. There will still be emails to answer, conversations to finish, tasks you didn't get to today. Life won't pause simply because you spent time thinking about a visitor from another star. But in this moment, right now, nothing is pressing. In this moment, everything is quiet. Above you, the sky turns the way it has for billions of years. The stars hold their positions. The moon pulls on the tides. The planets glide through their orbits with perfect steadiness. And somewhere, far beyond the brightness of the inner solar system, the faint glow of 3i Atlas is trailing off into the cold, becoming smaller, fainter, softer. Soon, it will be just another piece of drifting matter in the great dark, unseen but continuing on its path. There is comfort in that kind of predictability. Comfort in knowing that the universe does not shift wildly or unexpectedly. Comfort in remembering that the sun will rise tomorrow exactly as it always does. Comfort in understanding that the cosmos is calm, steady, and indifferent to the noise of our days. Take a breath here. Let your shoulders drop a little. Feel how the edges of your thoughts begin to loosen. You've spent enough time thinking about distance and chemistry, about orbits and starlight. Now, you can simply rest. You might picture the comet's light growing dimmer as it moves farther out, dissolving into the wide, dark canvas of the sky. You might picture the stars above it. Stars that burn for millions of years longer than any trouble you will face, standing still on their long, patient timelines. You might even picture Earth itself from far away, a small, blue world turning slowly, cradling oceans, clouds, cities, quiet bedrooms, quiet lives. In that picture, everything feels gentle, manageable, safe. You are safe. The universe is quiet tonight. Nothing demands anything of you right now. The comet has completed its part in this story. All that's left for you is to let your mind settle, to soften the pace of your breathing, to ease into the comfort of a world that keeps turning even when you stop for a moment to rest. The night is long enough to hold you. The sky is wide enough to steady you, and the silence is deep enough to invite you into it. So let yourself drift a little. Let the images fade. Let the sound of the story dissolve into the background. Whatever waits for you tomorrow can wait. Whatever you didn't finish today will meet you in the morning. Right now, you are held in a moment of stillness, one that belongs entirely to you. Good night. Rest easy beneath the quiet sky.